Section 6, Spring Equations Calculations. So the two spring equations are force equals spring constant times the extension, and elastic potential energy, or work done in stretching a spring, is equal to a half times the spring constant times the extension squared. So F stands for force, measured in newtons. K is the spring constant, in newtons per meters. E is extension, sometimes compression in some questions, measured in meters. And EE is elastic potential energy, and that's the same as work done in stretching the spring, and that's measured in joules. So low demand questions, very straightforward. You just put your numbers in. You always write out the equation, put a box around the quantity that's asked for, underline the given values, and you just put them in. So the spring constant is 5 multiplied by 0.2, and that is 1 Newton. Next one, you are finding the force again. So you underline the given values. The spring constant is 2 multiplied by 0.4, and that is 0.8 newtons. This one, what is the work done? So you put a box around the work done, underline your given values, and work done is the same as elastic potential energy. So you put your numbers in. So it's 0.5 multiplied by the spring constant 25 multiplied by 0.3 squared, don't forget to square it, and that gives you 1.125 joules. That should say joules. Question 4. So you write down the equation, F equals KE, and this time you put a box around the quantity that's asked for, you underline your given values. This time they're asking for the spring constant. So you write out your equation, you put your numbers in, so the force is 12, so 12 equals the spring constant K, that you don't know, multiplied by 0.3. So to find K, you do 12 divided by 0.3, and that gives you 40, and the unit is newtons per metre. Question 5. This time they want elastic potential energy, which is a half times the spring constant times the extension squared. So you do the same thing. They're asking you for the elastic potential energy. You underline your given values, and then you put your numbers in. So it's 0.5 times the spring constant, which is 1000, times 0.25, and again don't forget to square it, and when you do that, that comes to 31.25, and the unit is joules. Hey, question 6. So these are standard stroke higher. You've got to know the equation and change the subject, and you've got to watch out for something extra, often a unit conversion. So book your equations. You are asked for the spring constant, so you put a box around that. You underline your given values, and you should notice straight away that you've got 50 centimetres, you're going to have to convert that to metres, and you've got 2 kilonewtons, you're going to have to convert that to newtons. So you write out the equation, F equals KE. You're given a force of 2 kilonewtons, so that's 2000, equals the spring constant that you don't know, multiplied by, and you convert that to metres, which is 0.5. So to find the spring constant, you do 2000 divided by 0.5, which is 4000 newtons per metre. And remember what spring constant means. It means how many newtons are needed to extend the spring by 1 metre. Question 7. So box around the quantity that you asked for, underline your given values, and again you should immediately spot that that's in centimetres and not in metres. They're asking you for the work done. They give you the work done. That, remember, work done is the same as elastic potential energy, so that gives you a clue you're going to have to use the elastic potential energy equation. So elastic potential energy is the same as work done, so that is 2000. So you write 2000 equals 0.5 times the spring constant that you don't know, multiplied by the extension squared. Don't forget to convert it into metres and don't forget to square it. So you've got to get k by itself, so you've got to divide both sides by 0.5 times 0.24 squared. So you've got to calculate the bottom half and make sure you do 2000 divided by all of that, and when you do that you get 69444.4 and the units of spring constant newtons per metre. Okay, with this one there's actually a little typo here. It should say a mass of 200 grams, so this is quite a complicated one. You've got to start off by converting that mass into a force. So you're going to start off by using weight equals mass times gravitational field strength. So 200 grams is 0.2 kilograms multiplied by 9.8. That gives you a force of 1.96 newtons on the end of the spring. The question is asking you for how much work is done, so it's basically asking you for the elastic potential energy. But in order to find that, you've now got to find the spring constant. You're given the extension, 10 centimetres, but you've got to work out the spring constant first. So you're going to use F equals KE next. You know that the weight on the end of the spring is 1.96, so that's your force, equals the spring constant multiplied by the extension here, which is 10 centimetres, but you've got to convert that into metres, so that is 0.1. So to find the spring constant you do 1.96 divided by 0.1, that gives you 19.6 newtons per metre. You then substitute it into elastic potential energy equals a half times the spring constant times the extension squared, so that's 0.5 times 19.6 times the extension, which you used before, and don't forget to square it, and that gives you 0.098 joules. So that's quite a hard one. Okay, and the last one, question 9. So it's asking you for the work done again, so you're going to be using elastic potential energy. Underline your given values, so you should notice that the force is in kilonewtons and they give you the spring constant. So you're going to use F equals KE first because you need to find the extension. So the force is 2.5 kilonewtons, which is 2500, equals spring constant of 2000 multiplied by the extension. So the extension is 2500 divided by 2000, which is 1.25 metres. Then you substitute that into elastic potential energy, or work done in stretching the spring. So it's 0.5 times the spring constant, which is 2000, multiplied by 1.25 squared, and that gives you 1562.5 joules.